Here's a thought. What if the next great leap in space exploration doesn't come from a new rocket engine or a faster launch vehicle, but from a printer? It sounds strange, right? After all, 3D printing began as a way to make plastic prototypes and small design models. But in the past decade, it's evolved into something far more powerful, a technology that's quietly reshaping how we build, how we design, and soon, how we explore the universe. A recent review in Advanced Engineering Materials describes how additive manufacturing is becoming central to space exploration. It's being used to print rocket engines in a single piece, satellites that can repair themselves, and even the first generation of habitats made from lunar dust. So today, let's unpack what that means. Not just for engineers, but for anyone who's fascinated by how innovation changes what's possible. Because the future of space travel might not be about getting there faster, but about building once we arrive. Let's start with a paradox. What if the most precious cargo on a space mission isn't a tool or a tank of fuel, but the ability to make both? Right now, every single component that leaves Earth has to justify its weight. Every nut, bolt, and circuit board adds to the launch bill, which can reach up to $10,000 per kilogram. Engineers spend years optimizing every gram. But additive manufacturing turns that model on its head. Instead of sending complete systems, we can send a printer and feedstock and let astronauts manufacture what they need when they need it. This is called in-space manufacturing, the ability to produce, assemble, and even repair directly in microgravity or on another world. In-space manufacturing reduces Earth dependency, lowers launch costs, and enables mission autonomy. That one line sums it up perfectly. And it's not just cheaper, it's transformational. Imagine a Mars mission where a connector cracks or a valve fails. Instead of waiting months for a replacement, the crew simply prints a new one using a digital model. And this ties directly into in-situ resource utilization, using local materials like lunar regolith as raw feedstock. It's the difference between camping with limited supplies and learning to live off the land. In the long run, that's the only way deep space missions become sustainable, by building what we need where we are. Now let's move from survival to propulsion. Rocket engines are among the most complex systems we make. Thousands of parts, extreme heat, and impossible tolerances. Traditionally, each engine required months of machining and hundreds of welds, but additive manufacturing is changing that equation completely. NASA's RAMP-T project, short for Rapid Analysis and Manufacturing Propulsion Technology, uses powder-fed directed energy deposition and powder bed fusion to print injectors, nozzles, and combustion chambers as single integrated pieces. They're using advanced alloys like Inconel 718, GR SOP 42, and NASA's GRX 810, which are designed to handle extreme temperature gradients without cracking. The results are staggering. These parts are lighter, stronger, and, according to NASA, up to 70% cheaper to produce than their conventionally machined counterparts. The RS-25 engine, once made from hundreds of welded parts, is now being produced with single-piece additively manufactured components. And this isn't just NASA. SpaceX prints its Super Draco engines entirely in Inconel, allowing complex cooling networks that would be impossible to machine. Relativity Space claims 85% of its Terran 1 rocket by mass is 3D printed, including its main structures, all built in under 2 months. And Rocket Lab's Rutherford engine, the first to use electric pumps, is almost entirely additively manufactured. So we've moved from welding engines to growing them, and that shift from mechanical assembly to digital fabrication isn't just about performance. It's about redefining what engine design even means, from engines to orbit. Let's talk satellites. In traditional manufacturing, a satellite is a patchwork of subsystems, separate structures, heat management systems, and complex wiring. With additive manufacturing, those barriers are dissolving. Today, engineers can print entire satellite frames with embedded sensors, conduits, and cooling channels, all in one unified build. The review highlights materials like Ti-6-4 and Windform XT, optimized for the vacuum of space. Light, stiff, and thermally stable. This not only reduces mass, it makes satellites smarter. By embedding sensors directly into structural components, these systems can monitor temperature, vibration, and stress. and even reroute power around damaged areas. Some next-gen CubeSats are now being designed with AM-integrated propulsion systems, like miniature green monopropellant thrusters printed in Inconel and titanium. And perhaps most impressively, satellites can now go from concept to orbit in under 2 months. That's an unheard-of turnaround. So when we talk about the new space economy, we're really talking about this: a world where spacecraft are self-aware, self-maintaining, and manufactured in record time. Of course, printing in metal, especially in space, comes with serious challenges. Porosity, residual stress, layer misalignment, they're the hidden gremlins of additive manufacturing. But here's where things get fascinating. We're now embedding AI and machine learning directly into the printing process. Advanced printers use sensors to track every layer: optical emission, thermal data, acoustic signals, and feed that into neural networks that detect flaws in real time. If a defect starts forming, the printer adjusts parameters instantly: laser power, scan path, feed rate. This is what the review calls autonomous process control. The goal is clear: printers that can operate without human supervision, even in deep space. Imagine a 3D printer on the moon that detects an error, corrects it, and keeps going for months on solar power alone. We're no longer teaching machines to follow instructions, we're teaching them to adapt. And speaking of lunar power, let's talk about the most unexpected building material of all: moon dust. NASA and ESA are already testing regolith-based 3D printing, using lunar and Martian soil simulants to print structural elements. By heating regolith with lasers or microwaves, it can be sintered into solid blocks, strong enough for landing pads, habitats, or radiation shielding. The European Space Agency's Moon Village concept envisions entire outposts printed from the local environment. These structures could be layered with hollow conduits for thermal control and radiation protection, the kind of design only 3D printing makes possible. The review calls this a paradigm shift toward resource independence. And it makes sense. Why launch concrete and steel when you can use what's already under your feet? It's the ultimate expression of sustainability, the moon, literally building humanity's next chapter from its own dust. But there's a catch, and it's not technical. It's legal. If a company prints a base on Mars, who owns it? The Outer Space Treaty of 1967 says that no nation can claim celestial territory, but it says nothing about private entities manufacturing or mining in space. The review warns that additive manufacturing blurs these boundaries. When you use local material, lunar regolith for instance, are you using it or owning it? And what about waste or contamination from space-based manufacturing? There's no global framework for accountability. So as AM technology accelerates, policy has to catch up. Otherwise, the first factory on the moon might raise more legal questions than scientific ones. It's a reminder that innovation doesn't exist in a vacuum, even when it's literally happening in one. And finally, the big one. The end game of all this innovation. The ultimate goal of space-based additive manufacturing isn't just printing parts, it's printing systems that can repair, recycle, and even replicate themselves. NASA and other agencies are already experimenting with closed-loop manufacturing ecosystems, where waste, failed prints, or old components are reprocessed into new feedstock. Combine that with AI-driven autonomy, and you get machines that can work indefinitely. Self-sustaining, self-repairing, and eventually self-replicating. Factories that aren't built, they evolve. The first industrial revolution was powered by steam, the next will be powered by sunlight, code, and powder. When that happens, space won't just be a destination, it'll be a workshop. A place where technology and environment merge into a living, productive ecosystem. So as we look toward the stars, it's worth remembering. The real revolution in space isn't about how far we can go. It's about how much we can build once we get there. Additive manufacturing doesn't just make space travel cheaper or faster, it makes it inevitable. It gives us the tools to stay, to adapt, and to thrive. And maybe the question isn't, how do we reach new worlds? Maybe it's, how do we build them? If that thought sparked something in you, follow for more, because next time we're diving into hybrid metal AM systems and how lasers, sensors, and AI are reshaping high-performance manufacturing here on Earth. Until next time, stay curious, keep building, and remember, the future is being printed one layer at a time.